Okay. Today we'll talk about some applications of rotational objects, rotational motion. Let us now at first solve this known example. We will talk now about the equation of motion. Equations of motion. Remember or recall the equations V2 is equal to V1 plus A divided by T. V2 squared is equal to V1 squared plus A x direction. Also, x is equal to x naught plus V naught multiplied by T plus half A T squared. We finish these equations. If we like to solve any example using this equation, it will be simple for us. These equations are for constant acceleration, but our acceleration today is angular acceleration. Let us now solve. You will see in the first page, there's an example. To use these equations, if we have an object at x1 and move to x2 with initial velocity is equal to 5 meters per second. What is the final velocity at the time period? I think it is given delta t is equal to 10 seconds. We have this motion. And the acceleration is 3 meters per square second. If we need to find the velocity later, we can find it using the first equation. V2 is equal to V1 plus AT. I will not write the formula. Let me also review this example. With rotational motion, we have the angle delta theta, and we have 2 points. Point number 1 with omega 1, and the point number 2 with omega 2. Omega 1 is given as 2 radians per second. Omega 2 is unknown. We need to find it. In the time period, delta t, this is the time, and the delta time here is 5 seconds. The acceleration, which is alpha, which is the angular acceleration, is equal to 0.5 radian per square second. We need to find delta theta and omega 2. In our example, we have the acceleration, which is 3. We have the acceleration, which is 0.5. But this is in radians and this is in meters. We have the initial velocity, we have the initial angular velocity. We have the time, we have the time. We need to find omega 2. Okay, we know these equations. And as I told you from before, we have the same set of equations for the angular motion. So we have these equations. Omega 2 is equal to omega 1, V2, V1, plus alpha t, plus the acceleration multiplied by t. It is the same. Also, we have omega 2 squared is equal to omega 1 squared, plus we have 2. Here, plus 2 alpha. What about x? X is theta here, or delta theta. Also, we have theta is equal to theta naught plus omega initially, or omega naught multiplied by t, which is omega 1, plus half the acceleration multiplied by the square time. Just the same, we have the same equations. We just change v by omega, the acceleration by alpha angular acceleration, and the x, which is the position, by the angular position, which is theta, sorry. Now, we need to solve the same set of equations. Okay, for the well-known equations, V2 is equal to V1, which is 5, plus the acceleration is given, which is 3, multiplied by the time, which is 10. This will be equal 30 at 5, which is 35 meter per second. What about the change in x, delta x or x2? Okay, x2 is equal to, or you need to solve omega 2 here. If you like me to solve omega 2, just like I solved this one, I will solve this one. Omega 2 is equal to omega 1 is given to plus the acceleration half multiplied by the time period, which is 5. Okay, it is 4.5 radians per second. This is the same. We just put the velocity and the acceleration and the time. Also, what about the change in position and the change in angular position? We have angular and linear. X2 is equal to x1 as given in the equation, the formula. X1 or x0 is fine. Plus V initially multiplied by T. V initially is 5 and the time is 10. Plus half multiplied by the acceleration, which is 3, multiplied by T squared, which is 100. This will be equal x2 205 meters. So x2 205, x1 is 5. X1 how much? Yes, x1 is given the example. I think I didn't write it here. X1 is 5. So delta x is 205 minus 5, which is 200. It's okay, we find it. Now we need to find theta. Theta or theta 2. Here. Or delta theta. Okay, delta theta. If I move this theta to the other side, it will be theta 2 minus theta naught or theta 1, which is delta theta. It will be equal to, I just move this to this side, omega naught multiplied by t. Omega naught, which is omega initially or omega 1, if you like, will be 2, multiplied by the time, which is 5, plus half multiplied by alpha is half also. This is alpha. And the time squared. The time is, how much is the time? It's 5. Squared. This will be equal delta theta is equal to 16.25 radians, which is the same. We know from before the linear solutions, and now we solve the angular solution. We have the same set of equations. Any question about that? Online? Any questions about that? It's just simple like that. We know these things. Okay. As we see, there is a relation between the angular motion and the linear motion out in the formulas and the way to solve these formulas. And also there is a relation between them using some other formulas and the relation. We know more of them, most of them. Now I will talk about the relation between the linear and angular motion. Now, if we have a circle, and this circle has a radius r, as we know from before, the total angle is 2 pi. And the circumference, which is S, the total S, is equal to 2 pi r. If there is an object, and this object is moving around this circle, it will spend a time. And the total time to rotate all the circle is capital T, which is the time period, which is the period. For example, the period for the Earth to go around the sun is a year. The period for the moon to go around the Earth is a month, and so on. So, if we like to solve and to find the velocity, this velocity is tangential. V tangentially for the moving object around this circle. So V tangential, as we know from before, it is the distance over the time. The distance is S and the time is the capital T. So the velocity, it will be equal to 2 pi r over capital T. If we reorder this formula, it will be equal to 2 pi over T multiplied by R. 2 pi is a total angle, or a total rotation over the time period. This is a rotation per time, which is a velocity, which is the velocity during the total period. This velocity, we know it from before. We talked about it in the previous time. This is omega. 2 pi over T is omega. So the velocity tangentially, or the tangential velocity, is equal to omega multiplied by the radius of rotation. So there is a relation between the tangential velocity, which is a linear, and the angular. This is linear velocity, this is angular velocity. There is a relation between the linear velocity and the angular velocity, which is r, the radius. If this r is big, then v will be big with constant omega, and vice versa. Also, from before, we know that there is a centripetal acceleration or radial acceleration. If you remember the rotation of Earth around the sun, and we talk about acceleration radially is equal to v squared over r. If we have a rotating object around the center, there is acceleration toward the center of rotation. We have a radial. I remember that we solved many examples about this. And now we have the velocity v tangentially. So this velocity is the tangential velocity. now we can write the radial acceleration using omega, because we know V is equal to omega r, but it is a square over r. This is a radial. So this will be equal to omega squared multiplied by r squared over r. R with the square will be cancelled. So the acceleration radially can be also written by omega squared r. We can use any formula of them to compute our examples that depend on the givens in the example. Okay. Now, this velocity is constant, as we see. But what if the angular velocity is changing? What if omega is changing or the velocity tangentially changing? Then we have acceleration tangential. We have another one. Now we have acceleration to the center direction. But what if the object is changing its velocity during its rotation? Then we have another acceleration. And also we talk about this previously. If omega is changing, then V tangential is changing also. Then we have acceleration tangentially. So now if we have this is our system. This is the mass. We have A radially, which is equal to V squared over R, which is equal to omega squared R. And we have also acceleration in tangential direction. And this acceleration can be written as alpha multiplied by R. Now we have V tangentially is equal to omega R. And the acceleration tangentially is equal to the time derivative of the velocity is the acceleration. We need to derive this with respect to time. The radius is constant. And the tangent, the derivative of omega is alpha. Now we have the velocity tangential. The tangential velocity has a relation with the angular velocity. The tangential acceleration has a relation with the angular acceleration. We just need to multiply by R. We can compute, as we did from before, we can compute the total acceleration. Which is A total. And we can compute the angle phi. We did that from before. A total is equal to the square root, using the Pythagorean theorem, of AT squared plus AR squared. Also, we found phi from before also, which is the tan inverse of the opposite, which is AR, over the adjacent, which is AT. We did this from before. And we already solved examples of it. I moving not fast? We did take this from before. Okay, now we have an example on it. Again. Any questions so far? Any question online? This example, I think, we will find the requirements by these equations, which connect the angular and the tangential quantities. Okay. If we have a car moving around the circle with a tangential velocity, we have a tangential velocity and a tangential acceleration, and the radius is, I think, 25 meters. I'm talking about that. V tangential at that moment is 20 meters per second, and the acceleration tangential is equal to 2 meters per square second. Also, we have, as we know, we have acceleration toward the center, which is A R, and we have acceleration tangentially, which is AT. We need to find the final, or A total. And also we need to find the angle phi of that acceleration. Okay. We need to find omega, okay, alpha, AC, A total, and phi. Okay. The first one, omega. This is the relation. Omega, if Vt is equal to omega r, then omega is equal to Vt divided over r, right? V tangential over r, which is equal to V tangential is 20. And the rest just is 25. This will be equal, I think, to 0.8. Omega is how much the velocity? This is kilometer per hour. The velocity is given kilometer per hour. Then I need to convert it to meter per second. So V tangential is equal to, I convert it here, it will be 5.6 meter per second. Is that clear? I'm sorry for that. will be 5.6 divided over 25 will be 0.22 radian per second. This is omega. What about the alpha? Alpha, again, is A tangentially over the radius, which is AT is 2 over 25, which is the radius. This will be equal to 0.08 radians per squared second. This is acceleration per squared second. Any question about that online? Okay. Now we need to find AC. AC is equal to, we know that from before, it is V squared over R. Also, we have another relation for it. We have, it is equal to omega squared R. It is the same relation, but we just apply omega. Okay, this is V tangentially. It will be equal to VT is 5.6 squared over the radius, which is 25, which is the same as omega. We solve for omega. 0.2222 squared multiplied by 25, which is the radius. This one. This will give us the same value, which is 1.2 meters per squared second. This is A to the center of the rotation. It is a linear acceleration. It is not angular acceleration. Alpha is angular acceleration. Now, any question about that? Now we need to find A total. Okay. A total, this one. Now we find A radial, which is AC, A radial. A centripetal, we write it in general. A total is equal to the square root of AC AR square plus A tangentially squared. This will be equal to, just we need to apply the numerical values, 1.2 squared plus, how much that one? A tangential. It is 2. It is given from before. So A total, this is total, because this is tangential. So A total is equal to 2.3 meters per squared second. So this is 2.3. This is 2. This is 2. And that one is 1.2. This is 2.3. How much phi? Simply phi is equal to arctan or tan inverse 2. This is phi. It is the opposite over the adjacent. The opposite is AR. I'm sorry. This is the opposite. AR over A tangential, which is equal to, will be equal. We just need to apply the values. So phi will be equal to 30.96, almost 31 degrees. This is phi. Any question about that? It is just simple equation, simple relation. We need to do that step by step. And if you start solving this equation, this example, it will not take this time, this long time because of me, because I'm talking too much. Okay. Now we have an important application, a small application, which is a rolling motion. If we have a circle moving, how many rotations it will move during some distance. For example, we have this chalk. It will move, for example, maybe 20 times from here to here. But if we have this part of this circle, it will move, this circle will move half time, half rotation to pass this distance, because the change in, or that, yes, the change in radius. We will see that by an example. Any question about this online? If we have a car, we have now another example. If we have a car and has X wire with radius R, and this tire, not wire, I'm sorry, will pass a distance. This distance is 500 meters. During a time, this is delta X. During a time is 50 seconds. And the radius is 30 centimeters or 0.3 meters. As you see, the car has a velocity. This velocity is for the car. Is it given? We can't compute it. We can't find it. But I need you to give your attention to this point. If our car is moving forward and we can't find this, let us compute it. The velocity of the car is the distance. Assume it a constant velocity. It is delta X over delta T. It is 500 over 50 will be 10 meters per second, right? If the car moving in 10 meters per second to the right, it will not move in that velocity unless there is a point in that car move to the opposite direction. As we talked from before about Newton's third law, if I need to walk to the positive X direction, then my feet should move backward with the same velocity. And the car now, there is a point which is at the bottom of which is the contact point between the tires and the road. This tire point move backward with the same velocity. And this velocity is B tangential for this rotation. This is B tangential for that. It is a circle. It is a rotation. This is a tangential velocity at this point. And V tangential should be equal to this velocity, which is computed, which is 10 meters per second, to make the car move forward. If we need to accelerate the car and make it moving with 15 meters per second, then we need to give more power to the engine and to make the tires move faster, and V tangential for the tires will be more. It will be 15 to make it 15 here. Now, after computing the velocity of the car, we can find the velocity for the rotation tangentially, which is the same velocity, which is 10. Sorry. But it will be backward. We don't care about the direction. We need to solve some things. Now, we can find omega for the tire. Omega is V tangential over the radius. V tangential, we find it from computing the velocity of the car. It is V tangential over the radius. The radius is given, it is 30 centimeters. V tangential is 10, the same like that one. And the radius is 0.3. This will be equal to 33.3 radians per second. This is the rotation velocity. This is the rotation velocity for the tires. But clockwise. So the velocity clockwise will be a negative sign. If you remember that from before, when we taught you that the angle will be measured counterclockwise. Now our relation here, we have a minus sign. It does not exist here, but because I am not interested in it, I just need to compute the magnitude. Any question about this? Okay. What if I ask you, how many rotations of the tire will be occurred during this distance? So we have one rotation like this, will be like this. One rotation, two rotation, three rotation, four rotation, and so on. We need to compute these rotations. It is simple. It is simple. We can compute it using two ways. Okay, if we spread this circle, which is the tire, it will pass from here to here, for example. And we have another tire and another tire. How much this distance for the total tire? This is the tire. The total distance, this one, it is S, which is 2 pi r. So how many times we have along 500 meters? So number of rotations it's equal to delta x, which is 500, over S. It will be 500 over 2 pi r. R is 0.3. This will give us how many rotations? It will be 200. 256, I think, point. What is it? No, 65. Point 26. The unit of this is rotations. Rotation. Right. Now, is this point understood? I think we can compute it using another way. Oh, it's the same. What if we need to compute the period T, which is the period for each rotation? Now, the car passed the 500 meters during 50 seconds. We have 265.26 rotations. How much time for each rotation? We just the time period for each rotation is equal to the total time, delta T, the total time, which is, delta small t, over number of rotations, which is equal also to 2 pi over omega. Yes. We find that 2 pi is the total angle over omega. This will give us the total time here is 15. This is 15, and this is this number. 2 pi is 2 pi. Omega, we computed it, I think. That's omega. This will give us, for each rotation, 0.19. Is that right? Okay. Now, the tire of this car rotating, and for each rotation, the time will be like almost 1/5 of the second. It's fast. Okay. Any question about that? Like, again, we apply the same relations. We see the rotations, how many rotations during this process. We can compute it using geometry and mathematics. Now, we will move to another topic, which is the energy. And the most important energy in this section is the kinetic energy. And the kinetic energy, it is half mv squared. We need to apply it just like that. Now, can I erase this? Energy and rotational motion. We are talking about the kinetic energy. Kinetic energy is equal to half mv squared. It is well known. But now we learn a new thing about V. We know that V is equal to omega r, but it is squared. So square, square. Is that right? Then our kinetic energy now will be written in this form. Equal to half m is m. R squared omega squared. In physics, we can combine the quantities together and put parentheses anywhere we want. That is not forbidden. Now, this is the linear kinetic energy because we have a mass, ordinary mass, everything is a mass. And the velocity, which is a linear velocity. Now we have a kinetic energy. We have the half is a half. We have angular velocity. We don't have now linear velocity. Okay, where is the angular velocity? It is omega. It is simple to be understood. Okay. What about the mass? Now we have another mass. I will ask you, assume that we have, I'll show you something. Assume that we have a ball with mass 10 kilograms. It's heavy. And we need to rotate it around its axis. It will be rotated, okay? If we have another thing like this ball, but it is like this. It is a disc with mass 10 kilograms. And we need to rotate it around its center. This is a disc. Okay? And we have this ball, we need to rotate it, but around this axis. We need to rotate it like this. What if this ball is also just like this? Another shape. It is 10 kilograms. And we need to rotate it. Do you think the rotation is the same or will take the same energy? Or if you need to rotate them, you will spend the same energy each time. This one means that you need to move this ball like this. It will be difficult. Okay, because you need to move it long distance, and you need to make or do or apply more work to move it. But here you can just rotate it. Also here is simple. Also here you need to rotate it, but I think here it will be more difficult than this way. Okay. But now, if I order you or tell you, please move all of these objects linearly. You have the same mass, move them the same distance, 2 meters. You will tell me it's okay. All of them have the same mass. All of them, I will move them the same distance. And all of them, I will do the same work for them. Is that right? Because I'm moving them linearly. That's right. But rotationally, it is not the same. Because each time we have different R. This is R. This is another R. This is another R. And also we have another R here. So the rotation and the mass behavior during a rotation is different than the same mass during another rotation shape between this and this. So the mass during the rotation will behave different than the same mass during the linear motion. So our mass in kinetic energy from before, it is just a mass. If this mass is a point mass, or it is or if it is a cube, or a box, or if it is a person or a ball, it's the same. But during rotation, it is different. And you know that the dancer, when she rotates like this, different like this, it is faster or slower, right? That's because the rotation and the radius is different from case to case. And also now, because of that, now we have angular velocity, and we have another effect of the mass, which is mr squared. M is the mass. All these are masses. But R is different between them. This mass rotational effect is a new quantity in physics, in our physics now, which is moment of inertia. Moment of inertia is the rotational effect for the mass, because it depends on the radius of rotation. Is this idea is understood? Now, online, any question about that? We have the moment of inertia now. is a new quantity. Now we have the kinetic energy is equal to half mr squared multiplied by omega squared. This is the angular velocity. This is the moment of inertia, which is I. Its sample or is I, which is mr squared. Mr squared for a point mass or for a mass away from the center of rotation by radius r. This is the mass. Now, if we have more than one mass, from before, it is simple. The kinetic energy is equal kinetic energy for the first mass plus the kinetic energy for the second mass, and so on. Now, and the kinetic energy for the same mass is 1/2 m1 v1 squared plus 1/2 m2 v2 squared, and so on. But for this, it is the same also. We have m1 r1 squared, which is I1, multiplied by omega 1. If we have another object, then we have m2 r2. If we look for the sun, and we have here Mercury, Saturn, and Earth, for example, we have different R. Let us put this here. We have R1, M1, M2, R2, R3, M3. And we have the moon rotating around the Earth. It has its mass and its radius. If we need to compute the kinetic energy for all of them, we need to find I3, which is R3 squared M3. I2 is equal to M2 R2 squared. I1 is equal to M1 R1 squared. And the kinetic energy, the total kinetic energy of the system, we are not computing the kinetic energy for the sun. No. It will be equal to 1/2 I1 omega 1 squared plus 1/2 I2 omega 2 squared plus 1/2 I3 omega 3 squared. It's the same. And we just put I here for each one of them. Just like what we did from before for the kinetic energy in linear motion. We will apply an example of that. In this point, we assume the Earth mass is concentrated at the center, and we assume it as a point mass. Okay? But we have many shapes in our study. You can see that in page number 7. There is a figure from the textbook. You can see that if you need to rotate a rod, like where is the stick? If I like to rotate this, it will take, or I need to spin a walk different than if I need to rotate this. Also, that different than this. Also different than this. Okay? Because assume that their masses are the same, but the mass distribution different from object to another object. For example, for a point mass rotating along around a point, the moment of inertia I is mr squared, mr squared, mr squared. This is the general definition. But for a stick, you can see that a cylinder rod around the axis in the middle, it is 1/12. So for a stick like this, moment of inertia, if this needs to be rotated around its center, then the moment of inertia is equal to 1/12 m L square, I think. Yes. Its length is L. It is mr squared, but multiplied by 1/12. If we need to rotate it like this, not like this. Like this, it is 1/12. But like this, it is 1/3. If we need to rotate it around its edge, I will be equal to 1/3 ml squared. The rotational effect of the mass, of this mass, around its center is 1/12 ml squared. The rotational effect of this mass around its edge is 1/3 ml squared. It's different. Okay? What about different shapes? For a board, and this is a rectangular plane. A rectangular plane, just like this, around its center, it will be 1/12 multiplied by the mass, multiplied by the dimensions a squared plus b squared. Around its edge, like this, it will be 1/3 ma squared. Okay. For cylinders, for hollow cylinder around its axis, with two different R's, it will be one. I'll show you something. By the way, you will be given these relations during the exam. With my time, we didn't take them. This is R1. This is R2. The moment of inertia is equal to half m R1 squared plus R2 squared. What if R1 is equal to R2? I mean by that, it is just a shell. R1 is equal to R2, then it will be 2 R1. It will be divided like this. It will be mr squared, right? What if R1 goes to 0? It will be 1/2 m R1 plus R2 squared. If R1 goes to be 0, then all of this cylinder will be solid, right? R1 is equal to 0. Then we have 1/2 mr squared as given here. And so on. We are given for a sphere, for a sphere shell, or for a solid sphere. You can use them anywhere. I think we apply one of them in the next example. Let us up now. We have 15 minutes. Let us now apply this example on the kinetic energy. Yes, good. The kinetic energy, and we can compare our solutions from before and now, just like the example what we applied for the first example, which is V2 equal V1 plus 18, and I apply omega 2 is equal to omega 1 multiplied by alpha t. I compare it for you between the linear motion and the angular motion, and we will apply the kinetic energy for both of them now. We will solve double example. If we have a mass, which is a box, it is light. We have no friction. We have 3 points, 1 and 2 and 3. We have the same system, but we have disc or sphere. It is a sphere, I think. We have 0.1, 0.2, and 0.3. We have the same height. I don't know what the givens. Now, V1 is equal to 0. Here also, we have V1 is equal to 0. And omega 1 is equal to 0. We have omega now, we have rotation. We have V1 and omega also. We have omega 2 here. We have omega 3 here. We will compute just for 1 and 2. The mass is the same. It is 5 kilograms. And the altitude, h, for both of them is 3 meters. So we have now the same system, the same mass, the same object. The mass is 5 kilograms also. Omega 1 is 0. M is 5 kilograms. But now we have a radius for this object. The radius is R is equal to 0.3, the same as that car meter. Any question about the system? Any question about the imagination of this system? Now we need to compute the energy, the kinetic energy, the potential energy. It is simple. The mechanical energy at first point is equal to the kinetic energy at the first point plus the potential energy. We did that many times from before. This will be equal to 1/2 m v1 squared plus m g h. V1 is 0. This term is 0. We don't have any kinetic energy at the first point. M, so we have it 0 plus the mass is 5. The G is 9.8. The H is 3. This will give us the energy is equal to 147 joules. So the kinetic energy 0, the potential energy is 147 joules, which is the mechanical energy. What about the other system? It is the same. The mechanical energy at this point is equal to the kinetic energy at this point plus the potential energy at this point. But we have now another type of kinetic energy. We have two pockets for the kinetic energy. One of them is linear. The second one is what I'm asking now. We have a rotational object. This is a rotational kinetic energy at point number 1 because we have a rotational object. If you like, I will write it for you. This will be equal to 1/2 m v1 squared plus 1/2 I omega 1 squared plus m g h. The velocity at the first point is 0. Then the kinetic energy linearly, the linear kinetic energy is 0. The rotation now, omega 1 is 0. Then the rotational kinetic energy is also 0. We have a potential energy. M is 5. G is 9.8. H is 3, the same. It is equal to 147 joules. It is the same like that system. But we have two objects. Is that understood? We have the same energy. Now I will solve for the first system at point number 2. The mechanical energy at point number 2, it is the same at point number 1, which is 147, which is equal to the kinetic energy at point number 2 plus the potential energy at point number 2. This will be equal 147. The kinetic energy at point number 2, it is 1/2 m v2 squared plus m g h at 2. H at 2 is 0. This is 0. The potential energy here is equal to 0. The mass is 5. This is 0. I need to find the velocity. Just 147 multiplied by 2 over 5, it will be to v2 squared. Just take the root of that. V2 will be equal to, how much? Where is that? It will be 7.7 meters per second. The velocity of this object here is 7.7. It is just a linear velocity. This object is not rotating. It is just sliding, right? What about a rotating object? Is its velocity will be the same like that one? I will see. Now, at point number 2, we have another system to solve. We have a new term. Now, the mechanical energy at point number 2 is equal to the mechanical energy at number 1, which is 147, the same like that one, which is equal to 2 kinetic energies. The linear one plus the rotational one at point number 2, plus the potential energy. The potential energy, it is 0 because H is 0. Okay? Now, 147 is equal to the first kind of kinetic energy, which is a linear one, 1/2 m v2 squared plus 1/2 I omega 2 squared. We can compute I, and I computed there. I will compute it here. It is, I think, 2/5 m r squared. M is 5. R squared is 3 squared. So I will be equal to 0.0 0.18. What is the unit? I didn't talk about the units of the moment of inertia. It is mass, which is kilogram, r squared, meter squared. This is the unit of I. I can apply I here. The mass is 5. V2, I need to compute it. I find it. Then I have V2 and I have omega. Omega, I can't find and compute omega. Omega is V over R. Omega squared is V squared over R squared. R is given. V, the same V. So I will put I is 0.18. There are many ways to compute it. And V squared, V2 squared over R squared, which is 0.3 squared. Now I have just one variable, which is V2 squared. Omega, I can find it later. But now I need to solve my equation. Now 147 is equal 5 over 2 plus 0.18 over 2, this is 2, and 0.3 squared. All of them multiplied by V2 squared. Now I can find V2 squared. I'll remove these. I will keep the sketch. Okay. By doing this, I can find V2 for that ball is equal to 6.5 meters per second. We are done, by the way. The velocity for the box is 7.7. The velocity for the ball, the linear velocity, is 6.5. They have the same mass. They have the same initial motion. But there is a difference. The difference in velocity. If you are riding on this box and me riding on this ball, then you will pass me. You will win the race because your velocity is more, right? Your velocity is 7. This velocity is 7.7, but this velocity is 6.5. 6.5. Why? If we think in energy, where is our energy? Now here we have kinetic energy reflect this velocity because the kinetic energy is half m 7.7 squared. But the kinetic energy here is 1/2 m, which is 5, the same, but 6.5 squared. Where is the loss? Where is the waste? There's no waste. We don't have any friction force. We have rotational kinetic energy. We have the rest of our energy is 1/2 I omega squared. And if we like to compute the kinetic energy for both of them, here the kinetic energy is equal to how much? Who can tell me? How much the kinetic energy? It is simple. Yes? Right. Also, my kinetic energy is 147, but this is equal to linear kinetic energy plus rotational kinetic energy. The linear kinetic energy due to 6.5, it is 105 approximately. And 42 for the rotational kinetic energy. Now, our kinetic energy is good there. It is 147. But 105 for a linear, and our motion is slower as we see it. And 42 for rotation. Is that understood? Online, is that understood? It is on time. It is 1:15. I didn't think I can finish 9 pages in one lecture. I think I finished the chapter today. Any question online? So there is a short homework for this material. Will be posted this weekend, and you will have open time for it. If you need any more time to solve the previous homework, then it is okay. By the way, for those people who think that their degrees in the first and the second, their degrees are low, you can make your final very high to make your first and the second also high. This help yourself. It's your effort, not mine. You did everything. You don't think that I make the first and the second simple to make it. It is just your work. Okay? Any question? Okay. I think there is a quiz in the future, also in the weekend if you like. 3, 4, 10 questions. I don't know how much. Any questions, Mike? No, I didn't think so. I don't know. I have too much work to be done. Thank you. Okay, see you. Thank you for your best wishes. Bye.